Hey everybody, welcome back. Um, Today we're going to start chapter 23, where we are going to compare two proportions, um, and chapter 23 also covers comparing means. But for now, we're going to start with comparing proportions. So basically, we're asking the question, what if we want to compare two groups? Is this team better than another one, right? Does this basketball team average have more points on average than the other one? Um, or does this team have a higher proportion of wins, right? Than another one might be a good indicator of if they're better. Is my class smarter than another professor's class? Um, are women safer drivers than men? Right? We're comparing two different teams, comparing two different classes, and then comparing uh, based on gender, right? Women versus men. So we could collect proportions for one class. Maybe it's the proportion of students who got an A um, in one class compared to the other. Then we can take those two proportions and compare them, right? See if one is higher, see if they're the same or different, basically. And we have ways of doing that through means we've already learned about, such as confidence intervals and hypothesis tests. Um, so there are some requirements, right? Like we've seen before for proportions, each sample has to be a simple random sample. So now we need two samples, right? We need a sample for the first class and a sample of the second class. Um, the number of successes in each sample has to be at least 5. Um, number of successes. Or we've seen this before, right? Our sample size 1, right? So this N1 multiplied by our P hat 1. So basically the sample size from the first group, the proportion, sample proportion from the same group, first group, has to be greater than or equal to 5. And then that second sample size, so from the other class, and the proportion from that other class also has to be greater than or equal to 5. Yeah. Um, the number of failures. So basically, this is that same rule, but it's the sample size from the first group times 1 minus our sample proportion from the first group has to be greater than or equal to 5. Same thing for the second group. Um, the first population size is at least 10 times the first sample size, and the second population size is at least 10 times the second sample size. And the two populations need to be independent from one another. Okay, so this is kind of a new concept, right? So essentially, what we're going to be doing to compare our two proportions is we're going to be looking at the difference between the two, right? And we're going to construct confidence intervals at first, or in our hypothesis test, but um, for the hypothesis test example, our null hypotheses are going to be, are these two proportions? Hypotheses are worried about population proportions, right? Not sample statistics. Is that difference equal to 0? Well, um, I could move P2 over. Maybe you see where I'm going. If I add P2 on both sides algebraically, if their difference is 0, that basically means that these two things are equal, right? So also in our hypothesis test case, we might say, in our alternate hypothesis, we might say, sorry, lost my mouse again. In our alternate hypothesis, we might say, is P1 minus P2, is that not equal to 0? And if their difference is not equal to 0, by the same algebraic process with the same inequality, we're basically saying P1 and P2 are not equal to each other, right? So this is kind of a way to compare these proportions to each other. I'm sorry, I've lost my mouse again. So this is why we're looking at the variance of the difference of these two different variables, x and y here. Because we're going to see the difference a lot when we are comparing these either proportions or means, right? So there's this principle that the variance of the sum or the difference of two independent random variables is the sum of their variances. So what is this saying? It's saying the variance of the sum or difference of two independent random variables. So here we have the variance of the difference, right? X minus y. But this is saying that the variance of x plus or minus y, basically, right? Whether you're adding them together on the inside or you're taking the difference on the inside, the variance of the sum or the difference of x and y, it can be broken out into the variance of x by itself plus, right, the sum plus the variance of y. Um, and this will be very helpful for us, right? Because this thing in here can be difficult to calculate. But we know the variance of one proportion, right? So if we can just find the variance of one proportion, add it to the variance of our second proportion, well, we know how to calculate those two individual variances, right? Or those individual standard deviations. So when we go through this process, this will be very helpful for us. And so this kind of translates, right? The standard deviation, remember, it's just the standard deviation of x minus y. We'll kind of talk about that more on the next slide. So remember the variance of our sample proportion, we'll call it 1 here because now we have 2, is just equal to the population proportion 1, right? So the population that our sample came from times 1 minus that P1 over N1, our sample size. And then so variance for a second sample proportion, right? P hat 2 is basically equal to the same thing, but now we need a second population proportion, 1 minus that second population proportion, P2, over our second sample size, right? So the structure of the formula is exactly the same, but it's just a difference of what we're plugging in, right? So for P hat 1, we're going to plug in the corresponding proportion 1, P1, population proportion 1, right? And sample size 1. So then the variance now of the difference between our sample proportion 1 in our sample proportion 2, right, p hat 1 minus p hat 2 is just equal to the sum of their individual variances, right? So we've taken the variance of p hat 1 right here and the variance of p hat 2 and put it right here. So this is a very nice, easy way to calculate the variance of the difference, right, between these two sample proportions. We know how to calculate both of these things. And so it basically directly translates. We haven't really been using variances too much in this class or really at all, right? We've been talking about standard deviations. So basically the standard deviation of this is just the square root of the sum, right? So if the variance is equal to this, remember the standard deviation is just the square root of the variance. So note, we're not putting an individual square root under this guy, adding it to a second square root, right? It's the sum is all under the square root. And so if that's the standard deviation, then our standard error for our sample proportions, remember, we just plug in those sample proportions in place of the population proportions because for confidence intervals and hypothesis tests, we don't know about our population, right? We're trying to create a interval that contains the population for confidence intervals, or we're trying to make claims about our population in a hypothesis test. Excuse me. So basically, we can calculate a 101 minus alpha % confidence interval for the difference of two proportions with this formula here, right? It's very similar to the last confidence interval for one proportion formula, but now we just have the difference of our two sample proportions, and now we have the sample standard error, excuse me, again, for the difference of those two sample proportions, where we've used that property to say, okay, it's variance 1 plus variance 2, and take the square root with one z-value as well. Okay, so in the next video, we will work an example of this. It'll be basically the same process, right, as a confidence interval for one proportion, but now we just have some more things to basically plug in and calculate. Okay.